Okay, let me share my screen. So hello everyone, welcome to Multimodal Weekly. This is a virtual webinar series hosted by 12 Labs. We are an early stage Series A startup focusing on multimodal video understanding. This is in community initiatives that we've been doing over the past 2 years or so. We're meeting on a weekly basis to discuss a wide-ranging amount of topics. Obviously, inviting researchers to talk about application to talk about like their work in multimodal AI foundation models. We also have developers, startup founders from our community come in to talk about different application that they build in various verticals, open source projects they're working on. And oftentimes we have internal team members talk about like our product release tutorials, guys, building on top of our platform and API. Here's the list of some of the recent sessions of Multimodal Weekly. Trying to focus a bit more on the research side of things. So we have speakers coming from like, working on multilingual understanding to, Asians to segmentation, reasoning, object segmentation, dataset, continual learning benchmark, wide variety of things. So for today, we have a very highly packed session with 4 different presentations. And all researchers actually working on different aspects of video understanding multimodal AI. The first speaker is going to be Peter Yu, who come from University of Michigan. He will present his work called Espresso, which is a novel method that can extract and compress spatial and temporal information in videos separately. The second speaker is Jieneng Chen, who will talk about his work called ReXTime, which is a benchmark designed to rigorously test AI models' ability to perform temporal reasoning within video events. The third speaker is Zhuoyi Huang, coming from Microsoft AI at Stanford. She will present her work called MARPLE, a benchmark for evaluating long horizon inference capabilities using multimodal evidence. And we'll close out our webinar session with Jieneng Chen, who come from Johns Hopkins. He will talk about a recent study that he's been doing on the analysis of redundancy concerning visual tokens and efficient training within large multimodal models. So yeah, that's the high-level agenda for the session today. We'll have a speaker one by one. Each of them will have about 50 minutes for the talk. And for the attendees, feel free to send your question on the Zoom chat. And then after each speaker finish, we'll have like a short, maybe 3 to 5 minutes of Q&A session for each speaker. Yeah. So with that, I will stop sharing my screen. And I think Peter, you're the first one, so I'll let you share your screen, unmute yourself, and go ahead.
Great, thanks, James. Let me share my screen quickly. Hope everyone can see that.
Yep.
All right. Let me just turn the laser pointer. All right. Okay. Hey, everyone. My name is Peter. I'm currently a 5th-year PhD candidate from the University of Michigan. I focus on, applying VLMs for videos in the more embodied AI settings. And today, like James mentioned, I'm going to talk about my recent work called Espresso. The full title is High Compression for Rich Extraction from Videos for Your Vision Language Model. All right. So to start, I think everyone kind of knows this point in this meeting. Video powers perception in embodied AI. So currently, video cameras are the primary way in which embodied AI agents perceive the world, like the robot you see here. And these cameras have to run continuously. So we need to be able to understand long videos, not just like video clips that are seconds long. So let's look at how current VLMs handle long videos. And this is the canonical VLM for videos framework. So basically, there are T-frames are sampled from a long video. And each of the T-frames is independently encoded by a frozen VIT. And then you can see, each frame is represented by this series of tokens with the patch or the spatial dimension and then the temporal dimension here. And the encoded frames are then fed to the projector that project them into the word embedding space of an LLM. And then the projector may, simply just embed like an image VLM like lava, or pull some kind of pulling or some kind of compression going on. And then the pre-trained LLM, either frozen or fine-tuned, generates an answer based on the question, the projector frame features, and so on and so forth. And this framework is popular as it kind of gets around the problem of having to collect a large amount of video text data. And as you can see, image text data are more plentiful, so there are more LLMs and VITs for images. And then most of the current VLMs for videos kind of differ how they project these encoded frame features onto the word embedding space. So let's kind of take a look at a few of them and see what kind of challenges they pose of different projector design. So the simplest projector is what I call the naive projector, which is just a simple MLP-based projector that only changes the feature dimension of the encoded frames. So, and then it just kind of doesn't touch the temporal, the spatial dimensions. And Tarsier is one of them. And it has been trained on a large amount of video text data. And essentially, this type of naive projector is a direct extension of the approach introduced by Lava back in the day. And, it's basically a Lava that can handle multiple images. But the problem is that it's as you sample more frames, especially for long videos, you quickly run out of the context window of the LLM. So remember, a typical VIT encodes an image into hundreds of tokens, like say 300 or 500 or so. So just concatenating a few of them will get to thousands of tokens already. So in order to address that problem, some VLMs use what I call a pooling projector, and pooling projector reduces the number of video tokens typically by a linear factor, and then VideoChatGPT and VideoLlama 2 are two examples. So VideoChatGPT simply use mean pooling over the temporal dimension, the spatial dimension, and then VideoLlama 2 uses some convolution operations to linearly reduce over the spatial and temporal dimension. And there are lots of other methods. And this is based on the observation that there's so much redundant spatial information between video frames. And if you think about it, the neighboring frames in the video are extremely similar to each other. And it's certainly an improvement over the naive projector, but the number of tokens used to encode a video is still linear to the number of sample frames. So if you keep increasing the length of the video, the number of tokens to represent that video also increases linearly. So can we even go further and then actually break this linear relationship so the VLM can kind of scale to an arbitrary number of frames? And there are some projectors like that, what I call a fixed size projector, that compresses a sequence of video tokens, the frame features, into a fixed size sequence of tokens. So basically, it uses the same number of tokens to represent videos, regardless of their length. And one famous example is Flamingo, which uses what they call the perceiver resampler to compress the video tokens into a fixed size sequence of tokens. And there are other similar architectures like QFormer from Blip2, although Blip2 is technically just an image VLM. And this is actually very useful, especially if you're trying to interleave the video tokens and text tokens together. There are lots of practical reasons for that, which I won't go too much into detail here. But unfortunately, these projectors are not as good as other pooling projectors on long videos. So Flamingo focused on short clips of 8 to 10 seconds, sampled at like 1 to 3 frames per second. In my previous work, iLab, I also used this type of projector, but I could only really focus on short clips of like 8 seconds or so, sampled at 1 frame per second. So the question we wanted to answer in this work was, this, can fixed size projectors work on long videos just as well? So again, like this has very nice properties, and then it's very useful for embodied AI settings. So here's the proposed architecture, Espresso. Again, it's a fixed size projector that can handle long videos. So because we found that a naive fixed size projector used by models like Flamingo struggles with long videos, we wanted to see why that is, and then basically figure out what kind of information should be in this fixed length sequence. And our main hypothesis is that it's very important to extract features from the video that are very digestible to the LLM by separating out spatial and temporal features. And this is a common inductive bias in video models for action recognition. And also, on top of that, we want to remove redundant information too. So based on the prior work in two-stream architectures for action recognition from video, we first extract spatial information, spatial and temporal features separately using respective poolers. These are implemented as Q-formers, and you can think of them as like attention-based pooling. So then the extracted features, especially here, they're still linear, although the length is still linear to the number of sample frames, we then compress them into a fixed length sequence by respective compressors. And compressors are also implemented as Q-formers. And then here, this P and T are basically fixed constant model parameters. And finally, the compressed features are concatenated and projected to the word embedding space of the language model by the MLP. And we can even go further and divide the input frames into smaller segments, and the whole process can be applied to each segment and concatenated. So you end up with this n times p plus t tokens. And this is fixed, regardless of how many frames you sample. So let's see if it works at all. So before we can answer that question, we have to kind of dive a little bit into what a good benchmark to evaluate VLMs for long videos is. And that's because there's a phenomenon called single frame bias, where an image model with one frame can outperform a video model that has access to the whole video. And this has to do with the fact that many video benchmarks ask spatial questions instead of temporal questions. And what do I mean by this? So if you take a look at these frames, this is from the judo Olympic finals last summer in Paris. And a spatial question might be, how many judokas are on the mat? And you can answer this question just by looking at one frame. And the temporal question might be, how many times did the judoka in the blue gi attack? So in order to answer that question, you have to watch the whole video and then count, right? So we want to focus on these temporal questions. So why do video, just kind of a note on why video benchmarks focus on spatial questions that causing the single frame bias. I think it's partly because image benchmarks came first and spatial questions were important to them, obviously. There's no temporal questions in images. And I think it's also partly because temporal questions are just harder to come up with and answer. So again, just kind of wrap up, we want the benchmark to contain long videos. And again, most popular video data sets have short clips that are seconds long. And we want the benchmark task to require watching most of the video, so that there's no single frame bias, and then we focus on temporal questions. So there is such a benchmark called EgoSchema, which was released last year, and it's a multiple choice zero-shot question answering benchmark, and it introduces an interesting concept called certificate length, which is the length of the video that a human verifier needs to observe to be convinced of the veracity of the marked annotation. Basically, once they generate the questions, they kind of ask another set of annotators to look at the questions and see how much of the video they need to watch to answer the question. So they claim that, EgoSchema has, a lot longer certificate lengths, and with, video lengths that are a lot longer. They're about 3 minutes long, which is, respectable. So we took EgoSchema as our primary benchmark, and then but realized that Tarsier and VideoLlama 2, the naive projector model and then the pooling projector model I talked about previously, achieves pretty good results with just 16 frames, which kind of implied to us that EgoSchema may not be hard enough, despite its long certificate length. So we propose also a quick way to kind of increase the difficulty even more and call it a needle-in-a-haystack setting. It's a pretty common way to do it. So we basically concatenate randomly sampled videos to create one longer and more complex video. And we then indicate which scene where the question refers to in the prompt. Okay, so now the evaluation is set. So let's compare Espresso against other projectors. So we directly compare Espresso with Tarsier's naive projector and then the pooling projector from VideoLlama 2 called the SDC connector. And we basically swap out the projector layer in the canonical VLM and then compare them. And we're not using any segments because these don't support that. And then we use set PNT to 4 each, just a very small number of tokens to test the compression effectiveness. And then we initialize the VIT, LLM, and NLP actually with lava weights, and then fine-tune only the projector on the video text instruction tuning data from VideoChatGPT. And then we evaluate all these projectors on EgoSchema, both in the default and the needle-in-a-haystack setting. So here are the results. Just kind of go over the table quickly. It's NH refers to the needle-in-a-haystack setting. Naive means the naive projector from Tarsier, and SDC is the VideoLlama 2's pooling projector. And you can see that Espresso significantly outperforms other projectors in both settings. And it's the only projector that benefits from additional frames. So we now know that Espresso, despite using a fixed length sequence of tokens, it's able to outperform other projectors. So I'm going to go into a little bit of ablation studies. I want to be mindful of the time. But the first is does spatial compression help? And in order to test that, we basically get rid of the temporal compressor and then vary the number of the spatial tokens. And then everything else is the same. And we train a VLM in different settings, and then we evaluate on the EgoSchema in the default setting. So that's the results. So this is number of segments, and then we fix the number of sample frames to 32. P is the number of spatial compression tokens. And basically gray cells denote that there's no spatial compression because that's the number of tokens VIT uses to represent an image. And that the Pearson correlation coefficients are between the spatial compression rate, which is a negative log of P, and the EgoSchema accuracy score. So there's a lot of numbers here, but basically you can see that there's a positive correlation between the spatial compression rate and then the long-form video understanding capabilities. And then the correlation grows stronger as the number of segments increases. So why is that? And I think it's because we've hypothesized that it's because video frames that are temporally close to each other are extremely similar spatially. And this is even more pronounced when the number of segments is larger, as the frames within a segment are temporally even closer to each other. So as a result, the video tokens will contain too much redundant spatial information without compression and end up having a detrimental effect on the LLM's reasoning capabilities. So basically, the corollary is that the higher compression rate helps the VLM to learn to discard redundant spatial information and increase the spatial information density per token for video tokens, which leads to better long-form video understanding. Because these tokens are now more digestible by the LLM. So now we move on to just measure how much temporal compression help. And we basically do the opposite. We remove the spatial compressor and then bury the number of the temporal tokens. And here are the results. The total number of frames is fixed to 100 sample frames and 128 frames. And then the top row is for the number of frames per segment. And T is the number of temporal compression tokens as before. And then gray cells denote no temporal compression. And then the Pearson correlation coefficients are between the temporal compression rate, negative log of T, and the EgoSchema accuracy score. And you can see that there is a positive correlation between the temporal compression rate and the long-form video understanding capabilities, but it's weaker than that of the spatial compression rate. And furthermore, the correlation does not grow stronger as the number of segments increases. So why is that? So we believe that a similar dynamic happens here, where a higher temporal compression rate reduces the redundant temporal information and increases temporal information density per token, which results in better long-form video understanding. But the temporal information density in video frames is higher than the spatial information density, especially for sparsely sampled frames from long videos. So there is less redundant information to discard compared to the spatial information. So the positive impact is weaker. So finally, we kind of combine them together. We did see this result a little bit earlier. So we use both compressors, and then we compare that again. Compare Espresso with other pre-trained VLMs, Tarsier and VideoLlama 2, and we use this highest level of compression, which is T and P values are 4. And again, this is the default setting, and then a needle-in-a-haystack setting. This denotes the total number of frames, and then per segment number of frames per segment. And then the Pearson correlation are between the number of segments and the accuracy score. And so there's a positive correlation between the number of segments and the long-form video understanding capabilities of Espresso. Probably because Espresso essentially sees more of the video with more segments. And surprisingly, Espresso performs comparably with SOTA models trained on much more training data in the default setting, and performs them in the more difficult needle-in-a-haystack setting, which shows the effectiveness of Espresso. And then it's pretty interesting to note that the architecture that uses fewer flops like Espresso can perform well, which is kind of contrary to the common wisdom. So in conclusion, the inductive bias of processing and compressing spatial and temporal features separately is very helpful for the long-form video understanding capabilities of VLMs for videos. And encoding a video into a fixed length sequence is a viable approach, even for long videos, and which is great sign for scalability and video handling streaming videos in embodied AI. So that concludes my talk, and let me know if you guys have any questions. Thanks.
All right, thanks, Peter. Really appreciate you walking over the details. Since we're running like a little bit low on time, I think we can do the Q&A probably asynchronously via the Zoom chat. I also put the link to the archive page on the chat as well, so people can just read it and follow along. But overall, I think this is awesome work. Obviously, since we're focused on video language modeling, I think this is like super relevant for us, benchmarking, etc. So yeah, awesome
Great.
work.
Thank you.
Yeah, just curious, what's the inspiration behind the name Espresso?
The name Espresso. So because when I was working with my co-authors on this idea, we focus a lot on this idea of compression, and espresso, you gotta compress the beans, right, and extract the essence of the coffee beans. So I thought it's like a pretty clever way
Yeah,
of delivering the message. Yeah.
awesome. Yeah, yeah, love that point. I think yeah, both obviously like both spatial understanding and temporal understanding are very important, right, for long form video understanding. So this is obviously a very important work. Awesome.
Thank you.
So the second speaker, Jieneng, do you wanna go ahead and share your screen and go ahead with your presentation?
Sure.
Yes. Yep. It's a nice follow-up because you're also going to talk about temporal understanding within video, right?
Yeah. Okay. Can you hear me? And
Yep, I
can
see
you
it.
see my
Yep,
can you
yep.
see my screen?
Yes.
Okay, thank you. Wait a minute. Okay. Okay. Thank you for the invitation. I'm honored to be here today to share our work, ReXTime, a benchmark suite for reasoning across time in videos. This benchmark, published in the NeuralH 2024 dataset and benchmark track, designed to rigorously test AI models' ability to perform temporal reasoning within video events. I am Jieneng Chen, a master student at the Vision and Learning Lab at National Taiwan University, where I am fortunate to be advised by Professor Frank Wang. I collaborate with Jieneng Chen from Microsoft on this project, and together we develop innovative methodologies to push the boundary of video reasoning. Okay, today I look forward to discussing our approach, key findings, and the potential application with you. Let's dive into the detail of our work. Okay, we present ReXTime, a benchmark aimed at evaluating AI models' temporal reasoning capabilities in video events. ReXTime emphasizes across-time reasoning, where the question and corresponding answer are found in different video segments, simulating human-like comprehension. This type of reasoning requires model to understand cause and effect relationships across separate video parts, posing challenges for state-of-the-art multimodality language models. In this figure, a conventional QA features question and answer within the same segment. For example, a conventional QA may be like this: Why do we hold out a knife? And the answer is to sharpen the knife on the bottom of the plate. And we can find that the event mentioned in the question and answer are in the green segment. In contrast, across-time QA links question and answer from different segments. In this case, for example, the question may be, how can we cut out the tomato efficiently? And the answer could be, hold out a plate and sharpen the knife with the bottom of the plate. The example shows that only GPT-4 or grasped the context at the time we ran the experiment in 2024. Identifying that sharpening a knife with the bottom of a plate enhances efficiency when cutting a tomato. We provide three types of QA pair in ReXTime. Sequential are those with a before-after relation. Cause effect involves causal relation without a purpose. Means to an end refers to one event causing another with subjective intentions. ReXTime provides evaluation of multi-choice VQA and moment localization tasks. We require a model to select the correct answer from 4 options and predict the time span corresponding to the answer event. This figure shows the process how we classify event pairs within a video in the ReXTime. We leverage the LLM to annotate these 4 scrolls from 0 to 3 for each event pair. The first is directness. This criterion assesses the directness of causal link between events. For example, an event pair, a girl falls down, she's crying, scores high in directness, while another event pair, a man has dinner, he watches TV after dinner scores low because there's no strong causal link within events. The second is necessity. This criteria measures whether the second event is inevitable due to the first. That is, if the second event will still occur without the first. For example, an event pair, the marching band aligns in the street with instruments. A man passes in front of the marching band holding a camera. Scores high on directness, but the second event is not certainly a consequence of the first, resulting in a low necessity score. The third is proactiveness. Proactiveness evaluates whether an event is carried out with deliberate intention. Higher scores are given when there is clear evidence of premeditated action leading to the outcome. It can be viewed as proactiveness with regard of a successor event. For example, an event pair chopping tomato making a dish scores high in proactiveness because its human intention is clear. Last but not least, purpose. Even if the preceding event is executed with intention, the resulting event may not align with the original expectation. We ask the LLM to specifically detect whether the intention has been fulfilled. For example, an event pair adding ingredients into a cup, putting a drink on a table scores high in proactiveness, but low in purpose because the original goal was to make a drink, not to place it on a table. The relation can be further classified using the following rule. If the sum of directness and necessity score is below 4, it is regarded as low causality and classified in a simple sequential relation. For example, we have a pre-event having dinner and watching TV here. We could construct two QA pairs like what do someone do after having dinner? Someone watches TV. And what do someone do before watching TV? Someone has dinner. If the two events show a strong causal link, we further determine if the sum of proactiveness and the purpose is less than 5. They are regarded as low intentionality and are classified into cause-effect relation. For example, the cause event is a girl falls down, and the event is the girl is crying. And we can construct QA pairs in a similar approach, such as what do the girl falling down lead to? The girl cries, and why is the girl crying? Because she fell down. If neither of the above conditions is met, the events are in a means to an end relation in this figure. Chopping tomato and making a dish. We can have a QA like why to chop a tomato to make a dish, or how to make a dish, we chop tomato first. In ReXTime, we leverage MLM and LLM to generate QA. We first collect video data from with time annotation from two source video datasets, ActivityNet and QV Highlight. We propose a pipeline to categorize the event pairs and generate QA with view shot demonstration. To maintain the dataset quality, we introduce auto verification process for all data and human verification for validation and test data. With this pipeline, we can reduce about 55% of the data annotation cost. Let's dive into the pipeline process. In stage 1, we collect event pairs from source video datasets. Take the dense video caption dataset, for example. This kind of dataset, we have several captions and corresponding time segment annotations in a video. We first prompt LLM to pick two captions as an event pair within them. In stage 2, we apply taxonomy as mentioned above to classify the event pair into one of the 3 QA types. In stage 3, we generate QA from the event pair with in-context demonstration according to their QA types. We design different in-context demonstration for each of the 3 QA types. In stage 4, we conduct automatic verification by LLM to filter out some bad event pair examples. And additionally, to maintain the dataset quality, we further conduct human verification for validation and test data. In ReXTime, we provide more than 9,000 machine-generated training data, 900 validation data, and more than 2,000 test data. To quantify across-time reasoning for a dataset, we further introduce a new measure called question-answer intersection over union, QARU. QARU is calculated by dividing the intersection of the time spans of the question and answer by their union. A lower QARU indicates a greater need for reasoning across time, as it reflects smaller time overlaps between the question and answer spans. In a ReXTime benchmark, we evaluate models using two kinds of metrics, moment localization and VQA simultaneously. Additionally, we assess model using Grounding-VQA, where the answer is considered correct only if the alignment between the predicted time span and the ground span exceeds a predefined threshold. Here we demonstrate the result of frontier models on ReXTime and human evaluation. Result indicates that while frontier models show certain degrees of temporal reasoning, they struggle with more localization. The finding also reveals that recent LLMs are still far behind humans in both temporal reasoning and temporal reasoning VQA and movement localization. And additionally, we further prove the pure machine-generated training set is shown to improve the fine-tuning accuracy on reasoning across time tasks. We reported performance shift of two moment retrieval models, UniBTG and CGDeter, on moment localization. And we also report the results to grounding video LLM, VTime LLM, and TimeThread, which are capable of doing VQA and moment localization in the same time. The results provide a starting point for future study. In conclusion, we can say reasoning across time remains a challenge for current LLMs. ReXTime is the first benchmark for reasoning across time with more than 2,000 test samples. Also, we prove that our data generation pipeline is effective in enhancing reasoning across time in reasoning. For the future work, we wish to extend our framework to long videos, as the current dataset consists of videos ranging from a few seconds to several minutes. Processing longer video requires model to perform more complex reasoning across time. Another interesting direction is developing a framework for generating question-answer pair that require multi-hop reasoning, posing a greater challenges for intelligent systems. And additionally, our current test is limited to language-based events and can be addressed by a strong captioning model. To advance the benchmark, we believe incorporating more sophisticated visual reasoning, such as dynamic scene understanding and object interaction, will be essential. And thank you for the attention. This is our project page and my personal page. We have open source our dataset on Hugging Face and the evaluation script on GitHub. We also host a CodaLab platform to benchmark ReXTime. We welcome everyone to submit prediction to our benchmark. Thank you very much.
Awesome. Well, thanks, Jason.
Thank you.
Yeah. Since due to the time, I think we can, do the Q&A, async as well.
Okay, sure.
Yeah. Overall, I think, a lot of these, innovation in this work, I think, align pretty well with kind of what Peter mentioned in the previous presentation, right? We're focused on long form video understanding here and spatial and temporal understanding and reasoning. Visual reasoning. So I think it sounds like the way video LLM is moving is also incorporating a lot of the, I'd say, like chain of thought reasoning from the language model community, so that it can be it can tackle more complex kind of queries, right, from the users.
Yeah, maybe Espresso can also try to submit prediction to our benchmark.
Yeah, I'd love to try that. Yeah.
Thank you. Okay.
Perfect. So now I will pass it to the third speaker, Zhuoyi Huang. I think you're on the call as well. So let's go ahead and present your work on MARPLE.
Sure. Thank you so much. Share my screen.
Mhm.
Can everyone see this?
Yes, we'll see it.
Cool. All right. Thank you, everyone. Thank you, James, for inviting me for the talk. And my name is Zhuoyi Huang, and I'm currently a applied scientist at Microsoft AI. And previously, I worked with Stanford Vision Learning Lab, and I'm happy to present our work on a benchmark for long horizon inference. And our name MARPLE actually comes from a detective book, Miss Marple, if you have read it. So it's about like causal inference and detective questions. So let's take a look. So I assume every day we always solve a lot of problems like whodunit. So for example, we may wonder who left the fridge open if you have a child or children and who spilled the food on the ground. Maybe it's your cat or your dog. But how do you like actually infer who did it? So actually human has the remarkable ability to reconstruct what happened and figure out who did it by drawing an intuitive understanding of the first physical world that around the human and how human pursue the goals within their environment, which is like we as like human understand human behaviors, and also we can integrating evidences across sensory modalities like vision, language, and audio. So to bridge the gap between how human and machine intelligence, it's crucial that we develop a AI model that are capable of performing such a long horizon reasoning based on multimodal information. And a long horizon here is like a different compared to like reason a image and reason a short, like a few second video, but it's more of like a long horizon, like step-by-step, like complex tasks. So MARPLE is a benchmark that we released, and we have all of the like simulator and data sets as well as methods open sourced and is accepted in NeurIPS 2024 benchmark. And it's a benchmark for long horizon inference in everyday and specifically for complex scenarios. And we introduce inference scenarios that evaluate a model's capability to solve whodunit style mysteries, where the goal is to identify who from some potential suspects as early as possible. So to give you a more concrete example of what kind of MARPLE-like task looks like, we can take a scenario who turned on the laundry. So consider there are two agents. You can see like your daughter and your, maybe we're too young for this, but maybe your cat and your dog. And you can see that they have different tasks. So for example, one of the agents will turn on the laundry, but we don't know who. So from time step 0, we can see that the agents navigate around the environment and change the environment states. Here, you can see that agent B opens the closet and picks up the clothes, and it moves around. So we are still like keep that question in mind, who turned on the laundry? It seems to be be like more likely the agent B is going to turn on laundry because it picks up the clothes. But actually we can see that agent A also picks up the clothes. And we can see that at this timestamp, agent B actually like deviated like it's not targeting the laundry machine, but it's actually agent A that turned on the laundry machine. So it's very challenged because it's very trivial. You cannot by just looking at one time frame to reason like who actually caused that outcome, but like you need to you need to understand agent A and agent B behaviors, and also do a long horizon like Monte Carlo tree search. So yeah, here is why we create MARPLE, and we ask the model and humans to answer this kind of questions at different time steps of the trajectory. So we average across different trials, like mental simulation of who might, what might be the trajectories, and we want to get the inference accuracies. So as the trajectory progresses, we see more evidences and we perceive more information. We can obtain a inference accuracy plot, and we expect the accuracy of the inference, like we have the right conclusion, agent A or agent B did it, that is the accuracy. So we expect the accuracy to increase as we reach to the end. And we hope that a stronger model could be able to make accurate predictions earlier on. So you can see the stronger model is actually the orange one, which is like 0.8 accuracy at just by seeing 3/4 of the trajectory. So you can see that the inference scenario challenges the model to first reason over a long time horizon, and to reason at a higher level, not just low-level pixel level, about complex scenarios. And it also challenges the model to integrate evidences from multiple modalities like visual, audio, and the language. So you might wonder, like, what could this apply to like real world applications? I think this could be also like inspiring to 12 labs. So let's consider embodied AI. You need like household assistants, and you need to infer causal dependencies between actions to complete a long horizon tasks. And you need to, for example, assembling furniture or cooking a meal. You need to also infer the outage ahead of time, which is also a long horizon reason problem. And for warehouse automation, similarly, we need robots in logistics centers to optimize multi-step workflows and to infer like long-term effects of the inventory movements. That's also crucial for healthcare, because like you can imagine all real-world applications are actually long horizon and like temporal information. So for clinical decisions, we can integrate multimodal patients' data to predict long-term treatment effects and personalized interventions. Similarly to drug discovery and development, we also can do mental health monitoring. And aside from those domains, it can also apply to supply chain, logistics, social science, policy, finance, economics, and more. So all of this will result in like how do we bridge the gap of machine to do long horizon inference as human do. So go back to MARPLE, we have key contributions like the following. We have a multimodal simulator, which we can hierarchically generate agent behaviors like as any like task as you can define. So right now we are just focused on household grid world, and we have this multimodal evidences generated along with the trajectories. And we also have like 5 predefined inference scenarios, which is targeting for long horizon inference, and which is vary in difficulties and is easy for machine learning and cognitive scene research to do those event reconstruction and multi-reasoning. And we also provide pre-collected data set for those. We have over 500 trajectories for different environments and for different layouts. And we generate those for you to use. And we have a evaluation metrics on how early the model can make correct inference. Lastly, we benchmark two AI baselines on the inference tasks. First, we used like Monte Carlo tree search with a learned agent models, and for the learned agent models, we use imitation learning to learn from the agent behaviors from the data set, and we train a VIT to encode all of the multimodal evidences and predict the actions for each of the agents. So we have an agent behavior model, and we use monocolor tree search to do the causal inference. Well, we also used language models like GPT-4 to compare to directly do the causal inference. As a comparison, we also conduct behavioral study with human participants and let human to participate to do the causal inference. So to evaluate the performance, we plot amount of evidences measured as the fraction of the trajectories that a model or human seen against the inference accuracies. Rather than focusing on the convergence itself, because we can observe most of the model will converge when they see the whole trajectory, but instead we evaluate how early the model can achieve a high inference accuracy. With that in mind, we see that humans, which is in the blue curve, outperforms both AI baselines in this scenario, achieving a 0.8 accuracy with only around 40% of the trajectory seen, which means that us human can only see less than half of the whole evidences to get the right inference. And across the 5 predefined inference scenarios, we observe a consistent trend where human always outperform both AI-based baselines in terms of performance and robustness. But here is also some failure cases. We can see that the GPT-4 actually is not as good as our trained agent policy model. It fails to converge for 2 scenarios. We can see that although like the GPT-4 sees all of the trajectories, it can still fail to arrive at the right conclusion. So this is very hard for even large language models. And this is likely stems because it struggles to reason about environmental changes. And that is actually very crucial for like mental simulation. And we can see that the simulation-based models, green one and the red ones, they always converge to 1 at the end, but they still struggle to generalize. And we further evaluate the simulation-based models with different modes of evidences and the generalization settings. So we can see that for human, it's always consistent. We can just to notice the number here, the smaller the better, because we want to see less amount of evidences to be a stronger model. So for human, the performance are consistent, either in distribution environments or out of distribution environments. And for our own model, we can see that adding more modalities like only vision, we need more like evidences like 0.85. But if we add audio and language, audio, which actually presents like what happened, which is like action atomic information, and language is more high level, like the goals. So adding those modalities, we can see a improvement of the model. But all of them fail to generalize because human can be consistent on like in distribution and out of distribution, but AI model as like the best model that we can achieve still fails to generalize to like out of distribution tasks. So we hope that MARPLE can facilitate future like AI and cognitive research science research to bridge the gap between artificial and human cognitive abilities in such a complex and real-world inference scenarios. And we have open sourced our code base and our paper and our data set. And to mention the simulator can be scalable and can be like extendable. So if you want to like add more tasks or add more tests, like generate more trajectories, feel free to do so. Yeah, that's all about MARPLE. And we hope this long horizon causal inference task could be a popular research direction in the future.
Great.
Yeah, thank you.
All right, thanks, Zhuoyi. I really appreciate your working over the project. It seems like there's a lot of people got involved with creating this benchmark, right? Was that a particular aspect that you focus on throughout the journey?
Yeah, so we have human participants from psychology school, and we have also some previous work on like creating the simulator for agent behavior generations, which called mini behavior. And right now we are focusing on like mostly the Monte Carlo like reasoning approaches and training like multimodal models and test out all of those like state-of-the-art multimodal models and train and find and try to make sure the agent policy models are best performing in our scenarios. Yeah, it's a like large project indeed.
For sure. And I guess another question from my end is, what are some of the other tasks that you're most excited about to extend this project further?
Yeah, so I think right now we are most interested in the household, like personal assistant doing house chores and like finish the tasks using robotics planning. So we are mostly focusing on long horizon planning, and some other interesting tasks would be healthcare, because there are a lot of research ongoing for like understanding multimodal information from patients and in a long horizon temporal way where you can see the drug and lab results from past hospital visits and observing the outcome. Can you like predict what of the interventions can be placed to prevent that outcome, or like what are the reasons or what are the like cause for the outcome? So yeah, those are like super interesting directions.
For sure. I think yeah, it's very exciting to think about like potential tasks that video understanding can incorporate, right, with respect to like causal question answering. Yeah, I think there's a question in the chat here from Peter.
Oh, yeah, I can answer this quickly. So the input is symbolic information about the real world. We have a 8-channel to encode the layout of the room and the positions of the furnitures and the agents, where they are and what are their states of the furnitures, whether it's open or not. Yeah, because this is yes, it's a series of symbolic representation of the visuals. Because we are not photorealistic, we're mainly focusing on the high level understanding. Yeah.
Great, thank you.
Great. And I think you also mentioned like embodied AI, right? Just like, very interesting application.
Yeah, embodied AI for sure. Yeah.
Awesome. Yeah, so I think we have like roughly 15 minutes left, so let's move on to the final speaker. So yeah, Jieneng, yeah, let's go ahead and talk about vision encoders.
Okay, hi everyone, and my name is Jieneng Chen, and I'm a PhD candidate at Johns Hopkins. So first of all, I want to thank James and 12 Lab for inviting me. So today I'm excited to talk about the research and advancements in scalable and efficient vision engine models. And so this talk mainly covering the empirical lessons for designing multimodal models. Okay, so this will include 2 of my work. And I will start by introducing scalable vision encoding for vision engine models, and I will then present the following up work on efficient vision encoding in large engine models. So my talk will be focused on scalability and efficiency. So I categorize the de facto training pipelines of multimodal large engine into 3 stages. So the first is pre-training stage, or stage 0 include the setup of an off-the-shelf large engine model and also a clip pre-trained visual encoders. They are both trained on web scale data. So to connect the 2 modality, we will have the training stage 1 that is multimodal alignments, and also stage 2 that is multimodal instruction tuning. We usually call this 2 stage as post-training of large language model. As you can see, the visual branch plays an important role in the pipeline. So the question becomes how to design a scalable visual encoder and how to learn a good visual representation. And so my first work mainly focusing on how to design a scalable vision encoders to seek how to design a vision encoder. We benchmark the encoder first. We benchmark the modern clip backbones, including vision transformer, COMNET, and CONNET. And we try to see their data scalability, model scalability, feature resolution, and architecture. We try to grab the good stuff from various models. So the first is data scalability. So empirically, the performance consistently increase as the scene samples increase. And for the model scalabilities, we found that we discovered that the hybrid model scale well in small data amounts, CONNET, but the VIT scale the best in large amount of data. So still the vision transformer demonstrate the most efficient scaling in terms of model parameters. And in the third part, we examine the feature resolutions. Is the visual feature resolutions, and we discovered that the higher feature resolution enhances the dense comprehensions, but the de facto output stride is 32. So we have the more fine-grained designs in our architectures later. And in terms of architecture, we found that the hybrid architecture is good in small model scales, but it is difficult to scale up the large hybrid model to billions of data. So we designed our model that is vitamin vision models in the vision language era. And so for macro level designs, we consider data model scalability, hybrid architecture, and three-stage design. For the macro level designs, we have designed novel convolutional block and transformer block. So for the data and model scalabilities, we adopt vision and transformer as the main stage, follow its scaling law. And for the architectures, we adopt we designed a mobile convolutional blocks on top of transformers. For the feature resolutions, we change the factors, downsampling ratios, and this lead to three-stage designs. For the macro levels, we designed a new mobile convolutional block that is simple, efficient, scalable. We tried a convolutional block is quite complex, but we designed a new block that is akin to the transformer block. So it is as simple as a feed-forward network. And for the transformer block, we decompose the feed-forward network layer into get linear unit activation that has higher capacity field parameter. And actually, this design has been incorporated to multiple large models as well. And so for performance, we call that it's time to replace vision transformer with a new architectures. You can consider vitamin, and it outperformed the factor of vision transformers by 2.4% average performance over like zero-shot classification retrieval task. And we can scale it down to like small data set and also small model size. The downscale vitamin-based version surpasses the top one solution of ICV 2023 data count challenging by 20% zero-shot image accuracy. That is quite impressive. And we can transfer our vision coders to open vocabulary perceptions. So include open vocabulary segmentation and open vocabulary detections. You can just replace the de facto scene or de facto vision transformer with our vitamins, and it achieve new state-of-the-art on 7 benchmarks for open vocabulary segmentation, and it also achieved the state-of-the-art results on open vocabulary object detection. And then we can transfer our pre-trained vision coders into multimodal large models. We can substitute the vision coders of lava to vitamins, and it is like 3% improvement on VQA, V2, and beyond. So the first of all, cover the foundation vision models in the vision eras. We empirically benchmark the different type of vision models, and we have practical experience on designing a vision coders in vision models, and then we transfer it to classification, detections, open vocabulary tasks, and also large multimodal models. Okay, so the second work is Lavolta published in New Release 2024. What I just presented is the yellow part visual encoders. These encoded visual features will be fed into large language models. I want to see the visual representation inside large language model, which is less studied. So in general, the input of multimodal large language models include visual prompt, system prompt, and question prompt. We want to analyze the attention allocation in large language model. So probably this work is somehow related to the Espresso work as well. And we discovered that the attention is mostly allocated to system prompt as seen in the arranged curve. So the visual tokens, the counterpart is seen in the blue curve are less attended. And this lead to the first finding that the visual tokens receive less attention from the answers token. We designed a simple visual compressor that is applied to cast large number layers, and the goal is to compress visual context for L layers. We applied a simple average pool on the over-the-shelf lava, and we found that the performance is high. So this leads to another finding that the visual tokens are super redundant in large models. And we conduct experiments on direct compressions on over-the-shelf models, and we found that the k-means is on part of attention-based compressions, and the average pool performs well as well. And if we training large model with compressor, we found that the simple average pooling is the best. That is the conclusion that the simple average pooling like have a stable compressed based training, and then we can derive a efficient training pipeline that we want to progressively compress the visual tokens in different training stages. So here we have 3 training stage. For the first 1/3 of iterations, we adopt heavy compressions. In the second 1/3 of iterations, we adopt light compression, and then we progressively decrease the compression ratios that can lead to a better performance in the test stage. So this is our designs of new progressive training stages. And so for compared to the traditional paradigms, we compress the visual tokens, so like enforce the efficiency, visual representation, and also we have a light compression in the final stage that can guarantee the performance as well. So in general, we reduce the total training budgets, and also we ensure that there is no information loss in the final stage models. So we can accelerate large language models with a high visual compression ratios, and practically we accelerate training and we accelerate inference latency. So in general, in today's talks, I want to emphasize that the visual encoding is important for scaling visual models, and we should take care of the 2 design spaces. The first is visual encoders, and the second is visual encoding in large language models. So that's it. Thanks for attending. Is there any questions?
Sweet. Just right in time. I think I put the chat on the chat there, a link to the paper as well. Vitamin, right? I think that's the name of the paper that you mentioned.
Yeah.
Yeah, I think we had like 1 minute left for the webinar. Any okay, Peter, I got a question here. Does vitamin?
Yeah, thank you for the questions. You asked, does vitamin include the progressive compression training? So actually, this is 2 work. The first is visual encoders, and we don't have progressive compression training for the visual encoders. Actually, we use like 300 GPUs like to train the visual encoder for 2 months. So we adopt the full schedules to train our visual encoders. And the second work, Lavolta adopts the progressive compression training, and this is conducted in my lab, so it requires much less computational efforts. Yeah.
Awesome.
Okay, so yeah, definitely definitely the link to progressive compression training is a QR code, Lavota. You can scan it. Yeah. Actually, this is a QR code for the Lavota work. Yeah. And
Awesome.
there are a few minutes left, and actually, my next projects are still focusing on the visual representations, but instead of visual encodings, we try to have generative visual representations. If you are very interested, you can check our works generating explorable words. That's given a single image input. We try to generate the full 3D words. That is also related to the Zhuoyi's work on the agents and mental models. Yeah. And yeah, thanks, James, include our work. Yeah.
Yeah.
And
Go ahead.
And actually, you are interested in embodied AI, so I kind of attach the figures. So basically, we use the interactive word generation model GenX. We can gather the image of observation in the first line of algorithm 2. So we gather the image of observations about the word when we understand the missing missing part of words that can derive a more robust imagination augmented policies for embodied AI. So actually, this is a systematic work for the vision model and also embodied AI and connecting the generative model as well. Yeah. James, do you have questions?
No question. I think I just want to point out, like, there's a lot of similarities between the presentation today. It looks like there's a lot of common interest in embodied AI, and I think, like, from the application point of view, I think medical AI, medical intelligence is something that I feel like both this work and the previous work is also touching on. So yeah, I just want to highlight that.
Yeah, sure. Yeah. Please feel free to reach out to me. Yeah, and yeah.
All right. Thanks, Jieneng. We appreciate your presentation. So yeah, that's goes up our webinar. Thanks to all the speaker again for presenting your work. The recording of this session should be available, within the next couple of days. So by early next week, I'll send the recording. So you can all share it on your social media. And then for the attendees, thanks for participating. Once again, we run the webinar this webinar series on a weekly basis. So yeah, we have more research and more application focused presentation over the upcoming weeks. So yeah, if you found this informative, good luck to have you join us again. All right. Thanks everyone.
Thanks, James.
Thank you.
Okay, thanks everybody.
Yeah.
Bye-bye.
Enjoy your weekend. Cheers.
You too.